Welcome students. Today we are discuss about the topic architecture of 8085 microprocessor. Okay. Student will be able to learn the following objective from this lecture. Architecture of 8085 microprocessor and demultiplex and multiplex the address bus and data bus. Architecture of the 8085 microprocessor as shown in figure. Okay, the 8085 microprocessor are divided in five sections. Okay, arithmetical and logical unit, timing and control unit, serial control, interrupt control. Okay, so as shown in, we are discussing detail. The 8085 microprocessor architecture consists of five parts which are as follow: register unit, control unit, arithmetical and logical unit, interrupt unit, serial and IO unit. So as shown in block diagram, okay, the register unit is there. So the accumulator and flag register are there. Okay, and the general purpose register B, C, D, E, H, L. The size of all the general purpose register is 8-bit. The accumulator size is also 8-bit. Okay, the register unit consists of the 6 general purpose data register, and these are register B, C, D, E, H, L. Okay, and as well as two internal register W and Z. The size of all the register is 8-bit, and there are two 16-bit register, program counter and stack pointer. The general purpose data register, the 8085 microprocessor consists of 6 general purpose data register to store the 8-bit data. It is very important section in 8085 microprocessor architecture. This register name as register B, C, D, E, H and L as shown in figure. During the execution of the program, the user can use this register to store a data or copy a data temporarily by using the data transfer instructions. Okay. These registers are of 8 bits, but whenever the microprocessor has to be handle the 16-bit data, they can be work as in a pair. So BC pair, BE pair and HL pair. So whenever the user is want to the store the 16-bit data, that time okay, our general purpose register are used in a pair: BC pair, DE pair and HL pair. The 8085 microprocessor architecture also have two internal data register. These register are W and Z. These register are used for the internal operation of the microprocessor and not available to the users. Okay, so these two register are basically to transfer the data internally. Okay, so these two register are not used for the I mean it is not for users. Microprocessor use these registers internally. For example, in this case the call and exchange instruction are used. Accumulator. The accumulator is a 8-bit register and it is a part of the arithmetical and logical unit. The microprocessor use this register to store the 8-bit data. It is perform the arithmetical and logical operation. The microprocessor store the result of every ALU operation or every arithmetical operation and logical operation. Final result stored into the accumulator. The program counter, it is a 16-bit register which deal with the sequential execution of the instructions. The register is a memory pointer. The memory location have 16-bit address, which is why this is a 16-bit register. The microprocessor use the program counter to sequence the execution of instructions. The function of this register is to point to the memory address from which the next byte is to be fetched. So when a data byte or machine code is begin fetch, okay, and the program counter is incremented one point to another point, means the next memory location. Instruction register and instruction decoder. The microprocessor performs the following cycle repeatedly: fetch, decode, and execute. So while the microprocessor are fetching the instruction from the memory, it is stored into the instruction register, and the instruction decoder is decode that instructions and store into the instruction register, and to send the necessary controls and timing necessary signal to the control and timing section to execute the instructions. Flag register. The ALU is also have the five flip-flops, okay, and this become the set and reset the after the operation. The value is according to the data condition of the result in the accumulator. So means all the flag are affected to the result of accumulator or content of accumulator, and there are different types of flag are there, okay. Zero flag, carry flag, sign flag, parity flag, auxiliary carry, and the bit position in, I means the flag register is bit oriented. The microprocessor use the flag to set and reset the condition. For example, okay, after the addition of the two number, if the sum in accumulator is larger than the 8 bit, then the carry flag is set, okay. And when the arithmetical operation like addition, subtraction, the result is 0, okay, then the 0 flag is set, okay. So whenever the arithmetical operation is performed and our answer is 0, I mean the content of the accumulator is 0, so 0 flag is set, okay. So as shown in figure, okay, this is a format of the flag register. So it is consist total 5 flag is there, okay, and cross is indicates that this flag is used for the user, so it is reserved for user, okay. So carry flag, the carry flag is indicates that whenever during a addition of subtraction operation a carry or borrow is there, okay, if carry is generated, then the flag will be set, and the flag also be set before the mathematically operation or external operand certain instruction as shown in figure, okay. So when we do the addition, okay, so now observe the last bit, both are 1 1, so the sum is become 0 and the carry is generated, okay. So that's why the carry flag is set, okay. Parity flag, the parity means the number of ones in a, okay, number of ones is available in our uh, content of accumulator, okay. And there are two types of parity is there: odd parity and even parity, okay. So when the number of ones are odd, so the odd parity is generated, and when odd number of ones is odd, so the odd parity is called, and when odd parity is there, so the parity flag is become 0, and when the number of ones is even in our result, okay, so it is called the even parity, and when even parity is there, so the parity flag is set to 1. Auxiliary carry, so it is show the as shown in example, whenever the carry is generated from D3 bit to D4 bit, so as shown in example, okay, the D3 bit both are 1 1, so the sum is become 0 and the carry is generated from D3 bit to D4 bit, so the auxiliary carry flag is set. Here a carry generated from the D3 position and, okay, propagate to the D4 position, the carry auxiliary carry flag is set. Now 0 flag, this flag is indicates that whenever the result of the mathematically as well as logical operation is 0, okay, then 0 flag is set, means the content of accumulator is 0, so 0 flag is set because the final our answer is stored into the accumulator. Sign flag, so this flag is indicates that when whether the result of mathematical operation is negative or positive. If the result is negative, then the sign flag will be set, and the result will be when the if the result is positive, then the flag is will reset. actually the bit is is affected of the D7 bit of accumulator. So as shown in figure example, see the so the example is given and all the flag is affected over. So here is carry is not generated. So that's why the carry flag is become 0. The parity is depends on the number of ones. Here is the number of ones is 6. So the 6 is our even number. So that's why the parity flag is 1. And even parity is there. That's why the parity flag is 1. Now auxiliary carry. So now observe the D3 bit. So the carry is generated from D3 bit to D4 bit. So that's why the auxiliary carry flag is set. And sign flag, so observe the result. The last bit D7 bit is become 1. So our result is negative, and when D7 bit is 1 is indicates that the result is negative, and when negative result is there, so sign flag is set to 1. And 0. So here is the our answer is not 0, it is a non-zero. That's why the 0 flag is not set. Interrupt section. There are 5 interrupts in 8085: trap, RST 7.5, RST 6.5, RST 5.5, and INTR. The trap is a non-maskable while other are maskable. When the interrupt comes on one of the pin of the 8085, the 8085 microprocessor suspend the current activity and save the status and jump to the specific address. And it is called the whenever the ISR is written. So ISR is a nothing but interrupt service routine. So at that location, the ISR is written over there. The jump address for each type of interrupt and their priorities as shown in table. So as shown in table, all the interrupts are given: trap, RC 7.5, 6.5, 5.5, and INTR. The priority level is also given. The trap has first priority, and the jump address is also given. So all the jump address is a nothing but ISR address. So the user is write down the ISR at that location. So whenever the trap is occurs, the microprocessor is jump to the location 0024H, and execute the ISR written over there. RST 7.5 is the second priority, and the address is jump address is 003CH. RST 6.5 third priority, and the jump address is 0034H. RST 5.5 fourth priority, and jump address is 002CH. And INTR, so fifth priority is there, and the address is given by the external interrupt controller like 8259. Serial control section. The serial control section in 8085 provides the serial interface through SID, serial input data, and serial output data pins. The timing and control section, it is provide the necessary synchronization signal to perform the internal operation as well as external memory and IO operation. Arithmetical and logical unit. The ALU is it is perform the arithmetical operation, like addition, subtraction, as well as logical operation and or, not. And ALU use the data from memory and from accumulator to perform the arithmetical operation. It always store the result of the operation in accumulator. So basically the ALU is perform the arithmetical and logical operations. And whenever the ALU is performed arithmetical and logical operation, final result stored into the demultiplex address bus and data bus as shown in figure. So our lower order address bus AD7 to AD0 is multiplexed with lower order data bus. The multiplex address bus and data bus AD7 to AD0 is used to transfer the data and address both. In order to perform the read or write operation, the memory device is required to identify the memory location, which is specified by 16-bit address. The higher order address is available through A15 to A8 address lines, and the lower order address is available through AD7 to AD0. The lower order address must be latch as it is required by memory device. AD7 to AD0 lines must be made free to transfer the data. So the ALE signal is used to demultiplex the AD7 to AD0. So the ALE pin is used to demultiplex the address bus and data bus. So when ALE is high, AD0 to AD7 is consist lower order address, okay, and A8 to 815 is consist higher order address. So we decode our address, and when ALE pin is become low, okay, so we fetch the data, okay, from this location, okay, and that time the data bus is coming into picture, and we fetch the data from that location. Thank you.